Hello and welcome to a video on circle theorems. Now what we're going to do in this video is we're going to use all of these circle theorems to calculate missing angles. Now whenever you get a question in an exam that requires you to use a circle theorem to calculate a missing angle, you need to make sure that you give a reason for your answer, because that's what the examiner's looking for in their mark scheme. Is they're looking for the reasons for why you're giving your answers. So you don't have to give these statements word for word, but as long as you identify the key words, then that's what the examiner is looking for. So what I would suggest is these questions that I'm going to go through in a moment, you can always come back to this page. So if you wanted to pause the video and come back to this page if you do forget what circle theorem that you need to use. And you can also use this going forward in your revision if that helps. So we're going to go through 10 questions. We've got 6 on this page and then 4 on the next page. And for each question, we need to calculate the missing angle and then give a reason for our answer. So question 1, find the size of angle ABC. Give a reason for your answer. So ABC, that's this angle here. Now I can see that we've got a diameter here. So this is a semicircle, and we know that angles in a semicircle are 90 degrees. So we can say that angle ABC is equal to 90 degrees. And for my reason, I can just say that angles in a semicircle are 90 degrees. Or angles in a semicircle are right angles. Question 2. Calculate the size of the obtuse angle DOF. So we've got DOF here. Now the reason it says obtuse angle and it doesn't just say angle DOF is because DOF could mean this angle here. Okay, but this would be a reflex angle. So the obtuse angle DOF is this angle here. So that's the angle we're trying to calculate. Now here we've got 2 points on our circumference, and we've got an angle at the circumference that connects to these 2 points and an angle at the center that also connects to these 2 points. And one of our circle theorems is that the angle at the center is twice the angle at the circumference. So we can say that angle DOF, so angle DOF, but it's going to be 2 times angle DEF. So that's 2 times 44 degrees. So that is 88 degrees. And our reason is that angles at the center are twice the angle at the circumference. Question 3, calculate the size of angle HGI. So HGI, that's this angle here. And we can see that if we compare these 2 angles, they both join the circumference at these 2 points. So we would say that these angles are in the same segment. So we know that angles in the same segment are equal. So this must be the same as this angle. So we can say that angle HGI must equal 37 degrees. And our reason is that angles in the same segment are equal. Question 4. Calculate the size of angle KLM. So KLM, that's this angle here. And this is very similar to this one over here, but it's the other way around. This time we've been given the angle at the center and we need to calculate the angle at the circumference. So instead of doubling it, we're going to half it. So angle KLM, but it's going to be 148 degrees divided by 2, and I think I can do that in my head. That would be 74 degrees. So we can just say the same as this, but just switch it round. So angles at the circumference are half the angle at the center. Question 5, calculate the size of angle QRS. So QRS, that's this angle here. And here we've got a cyclic or a cyclic quadrilateral. And we know that opposite angles in a cyclic quadrilateral add up to 180 degrees. So we can just take 104 away from 180 degrees. So angle QRS, which is going to be 180 degrees minus 104 degrees, which gives us 76 degrees. And if we put our reason as opposite angles in a cyclic quadrilateral add up to 180 degrees. Question 6, calculate the value of x. So x is this value down here. Now there's a few ways we could do this. I think what I can see is that first of all we can calculate this angle here, because we've got a triangle and we know 2 angles in the triangle. So let's just call that y for now. So we can just take these values away from 180 degrees. So we can say that y is equal to 180 minus 105 minus 25. So what does that give us? Well, 105 plus 25 is 130. So if we take that away from 180, we're left with 50. So 50 degrees. And now we've got y, we can calculate x, because these two angles are in the same segment. Notice they both subtend the same chord, or they both subtend the circumference of the same 2 points. So they must be equal. So x must also equal, well, we can say that x equals y, which equals 50 degrees. And our reason, well, I'm going to give both reasons. So the first reason was that angles in a triangle sum to 180 degrees. And my second reason was that angles in the same segment are equal. Okay, let's move on to the last 4 questions. So we're now on question 7. So question 7, calculate the value of x. Now, for this question, you may be a bit misdirected by this 72 degrees here, because this is absolutely doing diddly squat. Okay, we don't need to focus on this at all, because hopefully what you can see is a cyclic quadrilateral. And we know that opposite angles in a cyclic quadrilateral sum to 180 degrees. So we can calculate x by just taking 47 degrees away from 180. So we can say that x, let's actually carry on in that blue color that we were using for our values. So x is equal to 180 minus 47. And I can do that in my head as well. Well, that will be 133 degrees. And our reason is that opposite angles in a cyclic quadrilateral sum to 180. Question 8, calculate the value of x. So for this question, what immediately pops out to me is this tangent line here. So it looks like we're going to use the alternate segment theorem. And what we're trying to do is calculate this angle here. So what is the alternate angle to this angle? Well, if we go opposite, if we take that angle and go opposite to look at which chord we're connecting to, or which chord it's facing this chord here. So what we do is just look at the tangent, and the tangent connects to that chord and it forms this angle. So this is the angle that is equal to this angle here. So we're not given that angle specifically, but we can calculate it because we know that angles on a straight line sum to 180. So let's call that A for now. So we can calculate A. A is going to be 180 minus 62 minus 58. So 62 plus 58, that gives us 120. Take that away from 180, we get 60 degrees. So A is going to be 60 degrees. And then X, well, that's going to be equal to A. So X is equal to A, which is equal to 60 degrees. So for my reasons, well, first of all, I can say that angles on a straight line sum to 180 degrees. And in terms of the circle theorem that we used, all we need to state is the alternate segment theorem. So this particular circle theorem just has a name, so we can just state that name and that's good enough. Okay, we're on to question 9 now. So calculate the value of x. So we've got this 72 degrees here, and what I can see straight away is that we can calculate this angle, because we can see that this is the angle at the center and this is the angle at the circumference. So I can say that this angle, again, let's give that a name. Let's say that that's B. So I can say that B is equal to 72 times 2, because it's twice as big, which is 144 degrees. And I'm actually going to give the reason straight away. So the reason for this is that angles at the center are twice the angle at the circumference. And now I can calculate x, because what I can see is that this line here is a radius. This line here is also a radius, because they both meet the circumference. So we've actually got an isosceles triangle. So what we can do is, first of all, take this away from 180 degrees. So we can say 180 take away 144. Well, we're left with 36 degrees. And then, because we've got an isosceles triangle, we know that these two base angles are equal. So we can just divide this by 2. So we can say that x is equal to 36 divided by 2, which gives us 18. So it's 18 degrees. And we do also need to give our reason. So our reason is angles in a triangle sum to 180 degrees. And base angles of an isosceles triangle are equal. Now this second part about base angles in an isosceles triangle, you probably don't necessarily need that, but I've just included it just to be sure. Okay, the last question. Question 10, calculate the value of x. So this is the angle we're trying to calculate. Now I can immediately see here we've got a triangle in a semicircle. So this angle here must be 90 degrees. Let's write that down. So let's call that angle C. So angle C is equal to 90 degrees, and our reason is that angles in a semicircle are right angles. And now we've calculated angle C, we can calculate angle X because we've got two of the angles in a triangle. So to calculate the last remaining angle, we can just take these away from 180. So X, well, it's going to be 180 minus 90 minus 62. So that, well, this just gives us 90, take away 62, we're left with 28. So 28 degrees. And our reason is that angles in the triangle sum to 180 degrees. So just like this one over here, this 18 degrees was completely redundant. So just be careful. Sometimes the examiner may throw in a curveball, okay, but you don't always necessarily need to use all the information that's been given. So hopefully this video has given you a bit more practice with applying all of these circle theorems to calculate missing angles, as well as providing the reasons for giving your angles. In the next video, we're going to look at some exam questions on circle theorems. Look forward to seeing you then. Take care.